Hey everybody, Chris McClure here. We're going to now take a look at mathematical modeling. And what we're talking about here is using a mathematical function to describe some sort of situation to help us solve some sort of practical problem. So let's dive right into this. We're going to build and analyze functions here. So we're going to have three examples to illustrate the idea of mathematical modeling here in this section. And here's our first example here. Now, we have some point P with coordinates x comma y. And P is a point on the graph of this function here, y equals x squared minus 1. Now look down here. You see in blue the graph of that second degree polynomial function. Now what we're going to look at here is the distance between the origin, which we're going to call point O. There's the origin right down there that has coordinates 0, 0. So the distance between the origin and any point on the curve. And that straight line distance we're going to call D. So here's a kind of a depiction of what that might look like for some random point on the curve with coordinates x comma y, where x comma y satisfies the relationship y equals x squared minus 1. So we're going to answer some questions here. What is the distance between 0, 0 and x comma y when x is 0, when x is 1, when x is equal to square root of 2, when x is equal to any other number? We'll also take a look at where on the curve could you be in order to minimize that distance between the curve and the point. It'll actually be two places because of the symmetry of the curve with respect to y-axis. All right, so let's go ahead and dive right into this. Remember the distance formula? The distance between 2 points on the plane is the square root of the x minus 0, in this case, squared, plus y minus 0 squared. And where this comes from is, remember, the distance formula tells us to take the square root of the sum of the squares of the differences between the x coordinates plus the y coordinates between the 2 points. Well, 1 point is 0, 0. So it really comes down to just taking the square root of x squared plus y squared for this particular problem. Now, as just an aside, and I don't want to confuse this, but if you were measuring the distance between some point on the curve x comma y and any other point besides 0, 0, then the coordinates of that point would go here for 0 and here for 0 for x and y coordinates for that 1 point respectively. But in this case it's 0, 0, so we get the distance formula square root of x squared plus y squared. But here's a kick though. Remember that the coordinates of your point x comma y on the curve satisfy the equation y equals x squared minus 1. So what we're going to end up doing is replacing y in the distance formula here. Replace y by x squared minus 1. Okay? So when we do that, we replace y by x squared minus 1, and we're going to square it, and you get x to the fourth minus 2x squared plus 1. And when you combine that with this x squared, you get x to the fourth minus x squared plus 1, and take the square root of that. And this function right here, the square root of x to the fourth minus x squared plus 1, measures the distance between the origin and any point on the curve with x coordinate x. Okay? So that distance is just a function of the x coordinate. You tell me the x coordinate is, and I'll tell you the distance. So first of all, what if the x coordinate is 0? Meaning, what if we're right down here where the parabola bottoms out? So when you plug in 0 for x, here in this formula, you plug 0, 0, 1, square root of 1 is 1. So that distance is 1. And that should make sense because the distance between the origin and -1 on the y-axis is 1 unit. So it should make sense that this distance when x equals 0 is 1. Now what if x is equal to 1? Now here the parabola crosses at x equals 1, so we should really expect for that distance to be 1 as well. Because if you take the straight line distance between the origin and 0, 1, that distance is 1. And indeed, you plug in 1 for x, what do you get? You'll get 1 to the 4th minus 1 squared, that's 1 minus 1 is 0, and you get the square root of 1. So, again, the distance is 1. And in fact, if we were to plug in -1 and for x, we'd still get a distance of 1. But for all other points, the distance is some other amount besides 1. In fact, if you were plugging square root of 2 over 2, then what would you get? Well, just plug in square root of 2 over 2 for x. And let's see, you get here square root of 2 over 2 to the 4th power. And what is that? That's 1/4, right? Minus square root of 2 over 2 squared, that's 1/2. And then plus 1. And under the square root sign, you get basically the square root of 3/4. And when you take the square root of that, you get square root of 3 over square root of 4. But square root of 4 is 2. So the answer is square root of 3 over 2. And that is the distance between the origin and the point on the curve with x coordinate square root of 2. All right, any questions on how to do that? And then if you have any other point on the curve, you just plug in the x coordinate into this function right here, and this function right here will calculate that distance between the origin and that point. All right, let's now plug in this function here into our graphing calculator. Just understand this is a function of x. And let's try to answer the question for what x value will minimize the distance between the curve and the point. So will it be over here, down here, or will it be here? Will it be over here or over here? Well, let's see here. Let's go to our graphing calculator. So please pull out your graphing calculator. And we're going to go ahead and graph it, and you're going to see a picture like this. But let's do it together on our own graphing calculators. So we're going to plug in square root of x to the 4th minus x squared plus 1. So I've pulled out my graphing calculator here. Here it is. I've got the equation editor already opened up. So let's do square root of x raised to the 4th power and then minus x squared plus 1. Okay, enter. Now, I have reason to believe that the x value which minimizes that distance is going to be somewhere between -2 and +2. So I'm just going to set x minimum to be -2. Enter. X maximum to be +2. Enter. And let's just set x scale to be, say, I don't know, 0.25 maybe, which is 1/4. And y minimum maybe to be, I don't know, -1. Enter. Y maximum maybe to be, see, 3. Enter. And y scale maybe to be 0.25. Enter. So let's go ahead and hit graph. So here's that distance function. And notice that there are actually two relative minima, one right here and one right there. So let's go ahead and find those two relative minima. And you remember how to do that? You go second and then hit this calculate menu, which is the trace button. And then select option 3, which is minimum. And let's just go ahead and find the x coordinate for this minimum. And the minimum value over here will be just the negative of what we find over here on the right. So let's go ahead and use 0 as our left bound. Enter right bound. I don't know. Let's call it 2 maybe. Input y coordinate of 1 maybe as our guess. Enter. And our calculator will very easily find the x coordinate of that minimum value of the distance. And indeed, we see that when x is equal to approximately 0.7071056, that distance, which they're calling y, is equal to 0.8660254. And you also get that same minimum over here at x equals negative 0.7071056 with that same distance of 0.8660254. Okay? So there. And that kind of shows the same thing as what we got there, except this shows it blown up a little bit. All right, now let's move on to our second example here. This is a very common sort of puzzler that we have in math is, we have some curve on the plane, and we often like to ask, what is the largest rectangle that we can inscribe, or largest square that we can inscribe in the first quadrant between the x and y axes and the curve. And that's kind of what we're doing here. Let's read the example. A rectangle has one corner on the graph of y equals 25 minus x squared. And that graph is this blue curve right here. That's the graph of y equals 25 minus x squared. And that corner of that rectangle that hits the curve is right here. The other corner is right down here at the origin. And a third on the positive y-axis, and a fourth on the positive x-axis. And we're going to express the area of this rectangle as a function of x. Well, this corner point has coordinates x, y. But remember, on the curve, x and y are related by the equation that y equals 25 minus x squared. Now, the area of the rectangle is x times y, is width times the length, x times y. X times y, which is good. But remember, y is equal to 25 minus x squared. So you replace y by 25 minus x squared. And you get 25 times x minus x to the third if you distribute this x across this binomial. Now, what is the domain of this function? Now, remember, area is being expressed as a function of x. Now, as we look here, it probably wouldn't make sense for x to be less than 0 or greater than 5, huh? But let's just see what the algebra tells us. If you were to, set this area equal to 0, you would either have area being equal to 0 when x is equal to 0, which would correspond to having an infinitely thin rectangle going up and down the xy axis. Or you would have the area being equal to 0 at x equals 5 or negative 5. Well, we're not concerned about negative values for x, but when x is equal to 5, we have an infinitely thin horizontally oriented rectangle, which has a 0 area because it's infinitely thin. So in order for us to have a rectangle that has any sort of positive area, we would need x to be somewhere between 0 and 5. So this set right here is the domain of values for x for this area function. Okay, moving on here. Now we're going to graph this area function. Now, if we were to plug in that function, 25x minus x cubed, into our graphing calculator, and here in the x minimum is 0, y minimum is 5, looks like we're going to let y go from 0 to 50. This is the graph that we would see here. And then if we were to use the maximum function from the calculate menu, we could very easily find that the coordinates where the curve tops out, remember this curve is the graph of this area function, the function 25x minus x cubed. That maximum value occurs here. Here's the x and y coordinates. Meaning when x is equal to 2.8867521 approximately, the area is going to be 48.112522 units approximately. That is the maximum area of a rectangle, this 48.112522. This right here is the maximum area of a rectangle that we can inscribe in the first quadrant under the rectangle, or under the curve, I mean. For any other value for x here, we'll get a rectangle that has a smaller area. Okay? So this just about shows where you have x being approximately about 2.88, 2.89 right there. And so this rectangle right here has this area right here of about 48.112522. That's the largest rectangle that you can put in the first quadrant within the curve. All right, that's how you solve this problem. It's not too hard, folks. It's just a matter of translating the problem into some mathematical function or equation that you then have to solve or evaluate. Okay, moving along here. Here's our third and last problem. It's a bit of a brain teaser, but I'll talk you through it. So we have this playpen here, and this is a problem from, the early 70s. Interesting problem. Now, I remember as a kid being put in these sort of pens, and I thought it was perfectly fine, but, people would tell me later on that it looked like I was a little chicken or a little small barnyard animal stuck in a little pen. Oh, well, it's fun. I raise chickens at my house. Yeah. And we've got a pen about this size right here that we are keeping our chickens in. So when I was looking at this problem before presenting this to you, I was thinking about my chickens. Anyway, all right, well, so what we've got here, let's read through the problem. A manufacturer of a children's playpen makes a square model that can be opened up at one corner and attached at right angles to a wall. So imagine that this thing right here could actually be made into a square. Or it could be opened up and put up against a house. If each side is 3 feet in length, and then it's opened up and placed against the wall like you see here, we have a pretty good amount of area for a kid to play. Now imagine that we were able to bend the playpen out right there and bend them out so you can make a configuration kind of like this, in the hopes of actually creating more area for the child to play in. So what sort of dimensions would we need? Like, for example, if you were to draw these imaginary lines, like from here to here, for example, and then from here out to the apex of this triangle, that distance between this line right there and the apex of that triangle is called h, as in the height of a triangle. So what would h have to be? And what would x have to be, where x is the distance between these opposite sides of the rectangular piece? What would x have to be and what would h have to be in order to maximize the area for the child to play with? So we're going to build a mathematical function which models the area as a function of x and h, and then we'll of course eliminate one of those two variables so that we have just a function of one of those two variables. Okay, so let's just tackle this triangle first. See this triangle right here? Now if you split this big triangle in half, then you've got a right triangle. And remember, the Pythagorean theorem says that the sum of the squares of the legs is equal to the square of the hypotenuse. Now the hypotenuse is 3. And this height right here, that's h. Now x over 2 will be the length of this leg right here, if you see where my little pointer is. So we have 8 squared plus x over 2 squared is equal to 3 squared. That's a good equation. So then we could actually solve this equation for h. So we can move that x over 2 squared over to the right-hand side by subtraction, and then simplify. You could actually, write 3 squared as 9, rewrite 9 as 36 over 4, so that this whole expression now becomes h squared is equal to 36 minus x squared over 4. When then if you were to take the square roots of both sides, and remember h is positive, so h is going to be equal to the square root of 36 minus x squared over 4. But then, of course, the square root of the quotient is the quotient of the square roots. You get square root of 36 minus x squared over the square root of 4, which means you're dividing by 2. So this expression right here is the height as a function of x. So then what is the area of this larger rectangle? It's 1/2 times base times height. But the base of the big rectangle is x. And you've got the height right there. Here's the height. So the area of that triangle is going to be 1/2 times the base, which is x, times the height, which is the 1/2 times square root of 36 minus x squared. And then plus the area of this rectangle right here, which is going to be basically 3 times x. So 3x right there plus the area of the rectangle, which is this stuff right here, gives the total area for the playpen when you have it in this sort of configuration. So the question is now, what does x have to be in order to maximize that play area? Well, it's now easy. You set up the mathematical area function. So now you just need to maximize this function of x. So take a look at this. Just simplify this guy right here. 1/2 times 1/2 is 1/4. So you're going to have x times the square root of 36 minus x squared over 4. And so when you take that area function and simplify, here is that function. Now, what is the domain of this area? Meaning, what's the minimum and max values for x? Of course, x has to be greater than 0. But does it make sense for it to be any greater than 6? The answer is no. As a matter of fact, if you were to take the square root function here and take the argument 36 minus x squared, set that greater than or equal to 0, then you'll see that because it doesn't make sense for x to be negative, that only values of x between 0 and 6 will make sense for the domain of that function. So that's what we did here. We set that argument of the square root function to be greater than 0 and then solve for x. So it only makes sense for x to be between 0 and 6. And now we go through and maximize this function and pick out a value between 0 and 6, which will maximize the area. meaning we're going to maximize this function and pick out a value for x. So let's go ahead and do that. Now, we could try to plug in some different values for x, like for example, if x is 5, 5 feet between these two sides, you get something like 19.15, and you can plug in some different numbers like 5.2, 5.3, 4.8, whatever. Or you could just use some algebra. You could actually plug in that function, plug in this function right here, plug in this function in your graphing calculator, and set x to go from 0 to 6 in your window, and play around with some different y values, like let y go from 0 to, say, 20 for y min and y max. Then here you've got a graph of that area function. And then you use that maximization function from the calculate menu, that maximization utility, and find that maximum value point, which is going to happen at this x value right here, 5.5836276, and this area right here, 19.816513. So it turns out that when you place these opposite sides 5.5836276 feet apart, and of course these sides will bow out automatically, then you'll have maximized the area for that child to play in, about 19.8 square feet. And that's how you do that problem, folks. It's not that hard. It just takes some practice, okay? Here's the hard part. The hard part is thinking algebraically, coming up with a function which models that area, using your geometric skills. You know how to find the area of a rectangle, and you need to you know how to find the area of a triangle. You just need to use your algebraic skills to express those areas in terms of a variable, and then maximize that total area using algebra. And then when you get to calculus, I'll show you some techniques that will allow you to find that area without using a graphing calculator. Okay, folks, so that's algebra for you. That's I showed you 3 examples here where you can use algebra to do something useful. All right, folks. So that's it for this section and for chapter 3. And as of now, this is the end of the material that's going to be covered for the first exam, for the midterm exam. I know some of you have been asking me, and I've been flipping through the book, and I think that this right here is a good stopping point for us as far as the material for the first half. Now, I'm going to take a few days off, and I probably won't get back with you until maybe Monday. So you're going to have Friday, Saturday, and Sunday to get through a lot of the material that we've covered, and I know that we've gone through a lot of material fairly quickly. So your job for the next few days is to process all of this material, work through the textbook, make sure that you're reading and studying all the sections, and studying the examples, which, by the way, a lot of the examples you see on these PowerPoint slides. And then working through the homework in my math lab. I'll be posting a chapter 3 quiz here in the next few days, and I'll make sure that I post that announcement when I make that posting. And then I'm going to be working on putting up your midterm exam and putting up details about that, okay? So we're talking about a week from today is when I'll be putting that out. But hey, just watch for the email with all the details, okay? It'll probably be more than one email that it'll take to get all the information out. All right, so that's it for now. We'll talk with you later. Have a good weekend. Take care.